Let's continue. Okay. It's so this is like okay, a possible. This is the 3CNF expression, right? And we are talking about 1, 2, 3, 4, 5. We're talking about 5 click, right? 5 click. So suppose there is a 5 click in this graph. Okay. Then there are no edge between nodes for variables in the same class, right? We only connect to other from each literal. We only connect to the literal of the other classes, right? So there is no edge in the same class. So this k click must contain one node from each class. Is that right? Is that right? Yeah. 因为我们在一个 class 里面的那3个互相没有 edge 嘛，我们每一个都是连到别的 class， 跟它没有冲突的那个 literal， 对不对？所以如果说你有一个 5 click， 那这个5 click 那这里面5 click 的每一个 node 一定是从不一样的 class 来的，对不对？这第一点。The second thing, okay, nodes in click cannot contain variables and its negation. 就它不能互相冲突嘛，对不对？就是在这个 click 里面 in this 5 click, there cannot be, the variable and its negation, 对不对？你最多就是你是2个是同一个 variable， 但是你不会是譬如说 x 跟 x not x，because that's 有冲突嘛，冲突我们不会放一个 edge， 对不对？所以不可能。Okay, the nodes in click must then correspond to a satisfying assignment。就说每一个 edge。OK， 它就说你这个一定是有一个就是 correspond， 譬如说像这个，像这个就是你记不记得我们在开始的时候我跟大家讲说，我们有一个 possible assignment， 就是在这边嘛。特别，好像这个。True, false, false, true， 对不对 ？True, false, false, true. Come back here. True, false, false, true. So this, you see, this x, negative y, okay, not y, and not z. So if you want to select this x, this is true. This not y, this is false. Okay, you have to assign y to be false. Okay, not z, you have to select z to be false. And u, okay, this one you have to select u to be true. Okay, and that's it. Okay, so that's satisfying. Each 5 click correspond to a satisfying assignment. Okay, so this is true, false, false, true. Okay, so once you have this, okay, for each class, choose one node whose value is true. Okay, so you choose this one to be true. There are k classes, so this yields a collection of k nodes. And the assignment is consistent. There is an edge between every pair of nodes. So this constitutes a k click. Okay? 这个一定是要 consistent 嘛，这个 click 每一个 edge 之间都互相没有冲突，所以它一定是 consistent， 整个是 consistent。所以说你只要 assign 那个，就让每一个就是都变 true， 就结束了。Okay, so with this you can from this one is like you are mapping. You are mapping from here to here. You map and then you are able to find the solution. Okay, so this mapping from here to this graph take polynomial time, right? And then from this graph, if you are able to find the phi click, how to find the phi click? Doesn't matter. Okay, you don't need to provide an algorithm for this. Okay. You don't need to provide. You just need to know. Oh, if there's a phi click there, okay, from here you can map back to here. That's exactly what we are talking about here. Okay, so this mapping again is a polynomial time, and this one is the solution for this, right? So the whole process. Okay, these two mapping is polynomial time. And from here to here, okay, we don't need to provide the algorithm. But we know like for each instance, we can construct a graph. And when this graph has a solution, this one has a solution. Okay, if and only if condition. So we have the first one, we have the second one. So we know K-click is NP complete. Okay? I mean, if we don't have enough time, the class ends here. Okay? But we have about another half an hour. So I will try to talk about maybe 2 more NP complete problems. Okay? So again, let's try to reduce K independent set. Okay, try to reduce the NP hard problem to K independent set. Okay, so we need to show that first. We need to show K independent set is NP, and then we need to show it is NP hard. Okay, and what is K independent set? Here again we show. No, we use the 3SAT. Okay, for this purpose. Okay. So what is independent set? Okay, for any graph G, an independent set is okay. Oh, it doesn't have it does not have like the definition of this problem. Basically, independent set is the subset of the vertices such that, okay, all the vertices are, what should I say? Wait a moment. Independent set is that's vertex cover. Independent set is为什么把这两个定义给它搞混了 ？Okay, there are 2 problems. They are both NP complete, and they are very similar. Okay, one is called vertex cover, one is called independent set. Okay, what is let me tell you what vertex cover is first. Okay, vertex cover is like it's a set of like you select like the vertices. It's a subset of vertices such that each edge you can you can find one end in this set. Okay, that's called vertex cover. because it cover this subset of vertices cover all the edges. Okay. If I remember, independent set means like the node, okay, the set of nodes that do not share the common, do not share that have no edge between them. Do not have edge between them. So for example, here, this graph, you can see the green vertices, okay, C, E, G, H, J, they do not share any edge between them, right? Okay, if I remember correct. Oh, there's one more. A. I mean, it doesn't. The graph doesn't have to be connected. Okay, and then we need to show it is like you know, NP. So if you are given a possible solution, okay, then you know we need to be able to verify. Okay, this is an independent set. Then, you know, first you check, okay, the size of the S, okay, because it's a K independent set, okay. So this subset has to be of size K. So first check the size of this subset. Second, so this takes this much time. Second, check for every edge is instant on at least one node in S. Okay, and this takes like a number of edges to check, right? So the total time to check this independent set is big O V plus E. So this is like a, you know, polynomial time. And then, so we have this, the first one. The second one, we need to show it is NP hard. Okay. Again, we use 3SAT, okay, for this purpose. So this is a clause, NS the 3CNF, and then we need to construct a graph such that if it has like a K independent set, then we have a solution for here. Remember, it's true, false, false, true, right? Okay, the assignment. So here, okay, how do we construct this graph? For each clause, we construct a triangle graph with its 3 variables as nodes. Oh, I remember. Yeah, the independent set is like you pick the nodes that do not for each edge, there's a node that in this set, okay, and they do not share the same edge, okay. So, yeah, I think I forgot. I mean, to mention one like criteria here. Okay. So anyway, so let's try to construct this. We have like 3 nodes. I mean, click. Okay, 5 of them. Okay, because we have 5 like clauses, and then we add an edge between each node and its negation. This is exactly the opposite of the previous what we did previously. Okay, so you can see, for example, X. We have not X, right? So we need to add a link to here, and so on. This is X, it's not X, so we have 2 links between X and not X. Okay, and so on. So we have quite a few links between each of these 3 clicks. Okay? So a lot of edges. Okay? So now let K be a number of clauses. Okay. And then, okay, we claim, okay, there's a K independent set, to be exact, 5 independent set, because K is 5 in this graph, if and only if there is a satisfying assignment. First, suppose there's a K independent set, S in this graph G. Okay? You can imagine, because of how we construct this graph, at most one node from each triangle, right? You cannot have more than one node from each triangle, right? Because they are connected. If you pick one, you cannot pick the other two. Otherwise, it's not going to be independent. Okay? And since the size of S equal to K, okay, there are K triangles. So each triangle has to contribute exactly one node. Right? Okay. And then, if a variable x is selected in one triangle, then x bar will not be selected because we add an edge between them, right? Remember, for one edge, we can only select one end to this set, right? So, because of that, okay, there are no contradicting assignments. Okay, so we can set variable chosen in each triangle to be true, satisfying assignment by construction. So to be exact, we select X here, we select Y bar here, we select Z bar here, we select U here, we select Z bar here. And you can see that there are K clauses. So we select one from each triangle. Okay, so we have exactly K nodes. Okay, and then, okay, if we use X in any clause, we will never use X bar. So there are no edge among the nodes in S. So basically, like this is like there's no contradiction, so we are able to, if we select X here, so X is true. We select Y bar here, so Y is false. We select Z bar here, so Z is false. We select U here, so U is true. Okay, so once we have this independent set, we immediately know this truth assignment. Okay, and then we are able to map this back to here. Okay, so this construction is polynomial time. And once we are able to find the solution, this mapping is also polynomial time. So, yeah, we reduce the K independent set to 3SAT. And then, okay, we prove that K independent set is also ME complete. Okay? The next is K-vertex cover. Okay. Yeah. We did the following reduction in an earlier slide. Okay, K-independent set. Okay. K-vertex cover. It's like this. Okay. We want to use K independent set is already NP complete, right? So we can use K-independent set to prove that K-vertex cover is NP complete too. So, I mean, this is relatively easy, okay? First, I need to tell you, okay, we don't need to do anything, okay? The graph of the K-independent set can be used directly for the K-vertex cover. And then, okay, actually, let me put it this way. The definition of K-independent set and the K-vertex cover is pretty much the complement to each other. Okay, so for example, you see this green and these blue dots. If you union these two, it will be the whole graph, right? And the green nodes indicate a K-independent set, and the blue node indicates the K-vertex cover. Okay, according to the definition. Okay, according to the definition. So basically, okay, if you want to find a K-independent set, then you are trying to find this K is not exact K. It's the number of vertices minus K minus this K. Okay, vertex cover. Okay, if you are able to find such a vertex cover, I mean the complement, okay, of the vertex will form K-independent set. Okay, so this is because there's no need to do any modification. The mapping takes like a constant, constant time, and this one, okay, to here, you just check for every vertex if it is included here. If it's included here, get rid of it. If it's not, put it in the K-independent set. That's it. So it takes like a big O, number of vertices time, and that's it. And again, this is polynomial. So the whole thing, we are able to verify K-vertex cover is, NP complete problem. Okay? So we show its NP is easy. Okay, given candidate cover, we check every edge is covered or not. Okay, that can be done very quickly. Okay, again, this takes like a number of edge, big O number of edges. This much time, so it's the polynomial. Okay, the verification takes polynomial time. So it's NP hard. I already showed you. Okay. So although nobody has proved P not equal to NP, if you prove a problem NP complete, most people accept that it is probably exponential. Okay. So therefore, okay, it can be important for you to prove that a problem is NP complete. Okay. You don't need to try to come up perfect non-exponential algorithm. Okay, you can instead work on approximation algorithm. So what does that mean? If a problem is so difficult, we know like general, it's most likely you cannot find a polynomial time solution, right? So you try to come up with, at best, you can come up with exponential solution, right? But usually we don't do exponential algorithm. Instead, we use approximation algorithm. The approximation algorithm is polynomial, but it doesn't guarantee it always give you the best solution. Okay, but if the approximation solution is very close to the best solution, and it can be done in polynomial time, then it's usually acceptable. If you prove the problem is NP complete. Okay? So it's kind of, this is a comic, okay? So we know like this is like take a long time to solve it. Okay, brute force solution is n, factorial, and it's very, very bad. So if you use dynamic programming algorithms, you try to reduce it, but it's still like a exponential, right? Okay, you try your best to do this, but actually, we are talking about this is actually traveling salesman problem. Traveling salesman problem. Okay, the brute force solution is n factorial, and if you use dynamic programming, you can get it done like this much. Okay, this guy is traveling salesman. Okay, by the way, and to be honest, like nobody really travel to sell stuff, right? You just connect to the internet, sell it on eBay, right? I mean, on the internet, you sell stuff on the internet. So it takes like constant time to connect to the internet, right? So so basically like no salesman does that anyway. Just want to tell you, exponential time algorithm is still bad. Nobody accept that. Okay, so you don't work on the algorithm. Either you try to approximate the best solution, or you try to solve the problem in a different manner. Okay, because you want to travel, right? You just don't travel. You just try to use like another alternative tool to get the job done. Okay, so yeah. This one I can skip that. And then, as I said, like there are at least 3,000, but this number is growing every day. Okay, NP complete problem. So you can check out the Wikipedia for list of NP complete problems out there. So some reduction are very difficult. Okay, some are relatively easy. So many are easy once the key insight is given. Okay, so basically, this is about it for NP complete problem. There are other very famous NP complete problems, such as Hamilton path, Hamilton cycle, traveling salesman problem, the one that I just told you. Okay, traveling salesperson, subset sum. Okay, given a set of integers, does there exist a subset that adds up to certain target t? Okay, or 0-1 knapsack. Okay, when weights not just integers. Okay, if the weights are integer, there's a polynomial solution. And graph coloring. Can given graph be colored with k colors, such that no adjacent vertices are the same color? So these are a few famous NP complete problems, but obviously we cannot list all of them here because there are so many. These are just the famous ones. Okay, depending on your research field, you may be more concentrated on some of them. For example, take me as an example. I used to do like wireless networks. Okay, so the vertex cover becomes very, very important. Okay, because in vertex cover, I'm able to, we want to, find a subset that cover, make sure like all the vertices are either in this set or a neighbor of, one of these neighbor will be in this set. Okay, so if you are going to pick a backbone, if you want to use construct a backbone, network backbone, okay, using the vertex cover as your network backbone will be very good, right? Because you don't select all the nodes there. You are able to reduce the number of nodes, in the backbone. Second, like, it's each node will be either in the backbone or it is like next to a node in the backbone. So this is a pretty good property, but this problem is NP hard, NP complete. So usually there are like people trying, very hard to find an approximate solution for that. Okay, so that actually that's part of my PhD dissertation. Okay, so okay, this is a review for what we have covered. Okay, and that's it. Okay, the consequences. Okay, NP complete is a set of hardest problem in NP with these important properties. If any one NP complete problem can be solved in polynomial time, then every NP complete problem can be solved in polynomial time. And in fact, every problem in NP can be solved in polynomial time. In other words, P equal to NP. Okay. Or you want to prove exponential lower bound for any single NP complete problem. In that case, you prove P does not equal to NP. Okay. Okay. In this case, every NP complete problem is exponential. Okay. Either one of them. So therefore, okay, solve traveling salesman problem. Okay, in polynomial time, you prove P equal to NP and get retired rich and famous. Okay, that's it. And it's impossible to solve NP complete problem in polynomial time. Okay, is it so? No one has proved that. Okay, and no one has proved exponential lower bound for any NP problem. Okay, but most computer scientists, okay, believe such a lower bound exists for NP complete problems. This is just a belief. Nobody has ever proved that yet. Okay, so that's why. Okay, if you prove that, you win Turing Award. Okay, are all past problems in NP trackable or intractable? Okay, does P equal to NP or not? If someone found a polynomial solution to any NP complete problem, we know P equal to NP, but most computer scientists believe P does not equal to NP. So that's it for this chapter. So we still have like 5 minutes, less than 10 minutes. Any question in particular for this class? Because this is the last lecture. Next week is going to be the final exam. Any question?那记得我还会再 upload 最后一个 homework，OK？、那 due day 会是下个礼拜的礼拜5 ，OK？ 请大家记得，好不好？但你如果说你前面的 homework 已经，因为我们是多少？选几个 homework？ 选4个嘛？对，那我们现在给的 homework 应该比4个多很多了。所以如果说你觉得说你 homework 的那个 credit 已经够了，你不要写那也没有关系。但至少我给你们这个 homework， 你们可以大概参考一下，说不定对你们期末考准备有一些帮助，好不好 ？OK， 那还有什么问题？如果没有问题的话，那我们今天就到这边，好不好 ？OK， 谢谢大家。